Hello. Um, so this time we have created a project on Boots multiplier, and what it does is it takes two numbers which are 4-bit each, and it generates the output corresponding to that, and it generates basically an 8-bit output corresponding to that, which is a combination of both A out and Q out. So I'm going to show you, these are the actually intermediate registers which you can see. Since the Booth multiplier is computed in n number of stages, for example 4 stages will be taken in multiplication of two 4-bit numbers. So these are the intermediate registers, and I initially took a in register having a value of 4 tick B 0000, and this q in was initialized as 1 bit 0, and this was the mm was the multiplicand and q in was the multiplier. So what it does is what it does in the very first stage, it takes that input, and if the last two bits of this q temp register, which was actually the q in register, if the last two bit of this q in or q temp register was 0 1 or 1 0, then it performs a plus m and a minus m respectively, and after that it does the arithmetic shift right. And if the last two bits of this q temp or q in register is 0 0 or 1 1, then it does only the arithmetic shift right, and it goes into the next state, and it does this algorithm every time. I'm going to show you. I know this is so if we see the flow chart of this, for example, every time this q in register, q in or q temp register will be having these last two LSB bits as 0 0 0 1 1 0 and 1 1, and if these bits are 0 0 and 1 1, then it straightforward then it straight away does the arithmetic shift only, and it moves to the next stage, and then the value of the state decrements by 1. So if we are multiplying a 4-bit two 4-bit numbers, then there will be 4 stages, and even after every stage this n will be decrement to 0, and after this n is decremented to 0, then the final output will be stored in this 8-bit register. And I'll tell you that this 8-bit register is going to store the multiplication of our two 4-bit numbers, and these four basically this Booth's algorithm is a signed multiplier of the two numbers. So it does the sign multiplication of the two numbers that we have given. For example, if I give minus 7 into minus 4, so if I give minus 7 into minus 7 into 3, so it should generate 21. And as we can see, this initially I initialize this to 4 times 0, and q naught to 0, and I filled in multiplier in this q register, which is the q temp register. This whole is the q temp register of 5-bit, and I initialized this um, m register. M is the basically multiplicand register with this 0 0 1 1 with m, and I'm going to multiply it every time. I'm going to just see these last two bits, and depending upon these two bits, this a plus m, a minus m, and or only arithmetic shift right will be done in every stages. For example, this time since 1 0 was the last two bits, so a minus m was done, then arithmetic shift right was done, copying just the MSB on this a register, and and these 4 bits were shifted to this side, and these 4 bits were shifted from on these 4 LSBs of this q temp register. And initial again in the same way, like when I stored this number 8-bit number on this a and q temp register, and I got this last two bits as 1 1. So according to the logic of like Booth's multiplier, when we get 1 1, only arithmetic shift right should be done and no a minus m or a plus m should be done. And just because of this 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 uh, uh, um, we should we should only do this arithmetic shift right. So this MSB will be copied to this, and these 4 bits will be shifted to these 4 side, and these 4 bits will be shifted to these 4 sides. And similarly, like if 0 1 was the, and then this will be copied to the next state, and these input will be now checked for the last 2 bits. And since this last 2 bit is having 0 1, so we should do arithmetic shift right plus we should also do this addition of a plus m, and a plus m will be um, done first, and then this arithmetic shift right will be done. So a plus m would be done via the last value of this a and the value of m. For example, the m we took was multiplier we took was plus 3. So sorry, multiplicand was we took this multiplicand minus 7 was the value of m. So minus 7 is represented by 1001 in 4 bit signed representation. So 4 bit signed representation of m was added with the current value of this a, which was initially taken in the stage 2. And after doing this computation, we will again arithmetic shift it right, and we'll get this 9-bit number. And in the same way we'll get the final number as this. And I'm going to verify this with the FPGA board as well. And finally we will get this 9-bit output, which will be having 4 bits of A and 5 bits of this Q temp register. And since we did the multiplication in a signed manner, since we took minus 7 and we took 3, so our output should be minus 21. So this output, the final output that is generated, is also a signed output. So to get the original output of minus 20, to get the original output, we will again have to invert it, and we'll have to add 1 to it, so that we can get 21. And 21 can be represented as 1 plus 4 plus 1. So we'll get a binary value of starting from the LSB 10101. Again I'm going to show you. So in this, if I take again in this, if I take multiplier 3 in this side, and multiplicand minus 7 in these input, this is the 4 signed input, and this is the again 4 signed input representation, 4 bit signed representation of input. And if I'm going to do this, then again I'm going to get this output: 1110 1011 and 1, 1110 1011. And again if I see 1110, the final output that I got is 1110 01. Wait. So I'm going to give minus 7 on this, and I was getting output 1110 1011. So we can see that on the ASR ASR below, 1 is showing 1110 1011, and this is 0. Actually this LED, if turns to red, will show you output 1, and if it turns to basically green, if it turns to white, and it shows 1, and if it turns to green, it shows 0. So right now we are having 0, so we confirmed it. And now I'm going to confirm it 3 into 3 is I'm going to make this output is, so 9 I got 1 1 into 1 1, I got 9. Now I'm going to multiply it by 4, so I'm going to get 12. Now I'm going to multiply 7 into 7. Wait, so I got 49, cause 32 plus 16 plus 1 is 49. Thank you. And again, if I multiply it with, suppose I am going to multiply it with 4 this time. So only 4, 7 into 4 is 28. 28 is represented with 16 plus 8 plus 4. So 16, so 1 is off, 2 is off, 4 plus 8 plus 16. So it is showing 24, 28. So it is working correctly, as we can do the multiplication in the, and multiplication is showing the correct output. And I'm going to show you the code logic as well. Now final I'm going to do is 7 into 8. 7 into 8 is 56, and 56 is represented by 32 plus 16 plus 8, cause 8 plus 16 is 24, and 24 plus 32 is 56. So 7 into 8 is 56, and this 8, 16 and 32 is also showing 56. So this multiplier is working correctly, and this is also a signed bit multiplier. So if it exceeds 111 range, and it goes into say 1001, that is uh, minus 7 was multiplied with the 3, as we saw in the example. So we will be getting output as minus 21, which will be represented in this ASR below 1 as 1110 1011, and this final 0. And I'm going to show you this logic every time this sum and difference signal was generated in this in these stages, and intermediate q temp and the q inter values were shifted during the logic. And every time, this was the case statements which were used to basically shift and perform the addition. For example, if the last two bits were 0 1, then sum would be done, and after the sum directly I did the sum. I basically I continuously made these wires to calculate the sum and differences of every state for every time, and I was directly taking these sums and shifting it in these 0 1 or 1 0 states. And after shifting it, I was taking it in a temporary register, and temporary register was again invoked in the very next state. And in the next state, again it was taking the help of this sum and the difference and ASR, and this ASR a plus m, a minus m was done in the case statement. Only the initialization was done initially in the starting block of begin in the starting block of always of every state. So this was the logic, and this was the code as I initially explained you. And these were the case statements. Case statements were the one which were computing the values of uh, computing the values at the end of the stages based on the last two LSBs of q temp register. And the q temp and this q inter, every q registers were taken as 5-bit, as I told you, and this a in, a temp, a out registers were 4-bit each. And as we can see, these values like are, as always block is also showing that on every starting of the new stages, if the signals from the previous state is sensitive and it is changing, so this a in, q inter, and this a temp would also be generated, and the q temp would be generated if the sensitive signals declared in this always block is changing due to the previous in stages input change. So in this way, and in this way, and cycle, our output is calculated. Thank you.